So this problem says two large rectangular aluminum plates of area 150 centimeters square face each other with a separation of 3 millimeters between them. The plates are charged with equal amounts of opposite charge plus or minus 20 microcoulombs. The charge on the plates face each other. Find the flux through a circle of radius 3 centimeters between the plates when the normal to the circle makes an angle of 5 degrees with the line perpendicular to the plane. Note that this angle can also be given as 180 plus 5 degrees. Okay, so this is essentially a parallel plate capacitor charged, and the charges reside on the inner surface like so. The surface charge density is given by Q over area, which is 20 microcoulombs. We can write it like so. 20 micro, minus 6 coulombs divided by 150 centimeters square, which is that many meters square. So the surface charge density is 20 into 10 minus 2 divided by 150 coulombs per meter square. We'll convert this to 200 into 10 minus 3 over 150 coulombs per meter square, which is equal to 1.33 into 10 minus 3 coulombs per meter square. So that's the surface charge density. Okay. Now, find the flux through a circle. So we will need the electric field between the plates, and the electric field between the plates can be calculated using Gauss's law. Okay. So if you draw a Gaussian surface like so, so the dotted line is the Gaussian surface, and so Gauss's law says flux is equal to charge inside divided by epsilon naught, and the flux is given by E dot area, which is equal to the charge sigma times area, the area being this area. That's the area within the Gaussian surface, divided by epsilon naught. So the electric field is given by sigma by epsilon naught. Okay. All right. So now we'll find the flux through a circle of radius 3 centimeter between the plates. Okay. So let me redraw the diagram again. So there is the okay, and here's our circle. So there's the electric field in that direction, and now let me draw the circle in red ink, and this area, there's the area vector, oops, and there's the electric field, and this angle is 5 degrees. Alright, so the flux is given by E dot area, which is E times pi r square times cosine 5 degrees. Okay, so sigma by epsilon naught pi r square cosine 5 degrees. And what is r? R is 3 centimeters. So Let's go here. Flux is sigma by epsilon naught. Sigma is 1.33 into 10 minus 3 coulombs per meter square. By R is 3 centimeters, 3 millimeters. No, 3 centimeters. 10 minus 2 meters square, cosine 5 degrees, and epsilon naught is 8.85 into 10 minus 12 coulomb square Newton meter square. Okay, so flux should work out in Newton per coulomb meter square. So the Newton, one of the coulombs cancels, the meter square cancels with that. There's a meter square, so the units are all working out. Okay, so now let's calculate this. Before we do this, let's take care of powers of 10. There's 10 minus 3, there's 10 minus 4, that's 10 minus 7, and there's a 10 minus 12, so when that comes to the top, that gives us a total of 10 to the 5. So let's do again 4, 7, 3, 7, minus 7 plus 12 is plus 5, so 10 to the 5, 1.33 into pi into 3 square is 9 divided by 8.85, and Newton per coulomb meter square are the units. Oh, and then cosine 5. Alright, so let's see what does this work out to. Okay, so this works out to 4.23 into 10 to the power 5 Newton per coulomb meter square. Okay, that ends that problem.